Now, welcome back to this last little bit of the complications of using interrupts. And this is a pretty serious one, okay? Interrupts can occur at any time. So for instance, if you're doing an addition of two variables, the interrupt might happen halfway through. That's easily going to happen because they're asynchronous. All they're going to do is crash your party and stop you from doing what you're doing, perhaps sometimes halfway through while you're doing it. So let's have a look at the situation where this could arise. And so understanding first of all that the AVR memory is 8 bits wide and everything happens inside our microcontroller in 8-bit chunks. Okay. Now, of course, that's not the same for your PC, which has got a 32 or 64-bit width that it operates on. So this is only something that happens in our small microcontrollers, our 8-bit ones, or even some of the 16-bit ones. But nowadays, of course, we often use 32-bit microcontrollers as well. But these 8-bit ones are very common. They're very inexpensive and used widely. Okay. So we'll look at an 8-bit microcontroller and say we're manipulating a 16-bit variable. Well, what happens then is that it has to manipulate each byte of the 16-bit variable at a time. And thinking about this in terms of what it actually looks like, so it's got to add the low significant byte of one variable to the least significant byte of the other, and then it's got to see if there's an overflow, and then it's got to add the upper significant byte from each of the two variables and then add the overflow to that. So you can imagine there's multiple operations going on in this. Now, just because you've written x equals a plus b to do this in C, actually there are multiple instructions in machine code underpinning this, and the interrupt could happen at any time during that. And this is really an issue with atomicity. And atomicity is really related to the atomic size of your transactions inside the microcontroller. And of course, ours are 8-bit. And so if we're working with 16-bit variables, we have to be, or 32-bit variables, we have to be very careful about using interrupts, which are manipulating those variables. So let's try and give you an example of this. And I've got it here. I've got a interrupt service routine, which is increasing a 16-bit value by 1. Okay, and here in my function, whatever that is, I've got a process of copying this 16-bit value into another 16-bit value. It's just part of a function. So it could be something else, as long as we're working on, if we're working on this variable and this same variable is part of the ISR, this is where we get issues. Okay, it doesn't occur with every variable transaction and multiplication and addition we're doing, but if we're using that variable within our interrupt service routine, then atomicity is something that's incredibly important. And in this case, we're using a 16-bit variable, so our atomic size is 8 bits, so we've got an issue to think about. Okay, so let me try. I'm going to just stop the screen share. Let's and point towards my bit of paper here. Right, here we go. It's upside down. I'll just rotate my camera. Okay, and I will stop the share. So you should now see the piece of paper. I'll turn the light on the camera so it's a bit clearer. So we've got this variable. Here's our variable. Remember, this is a 16-bit variable. I'm going to call it time delay. It doesn't really matter what I call it. It could be X, Y, Z, okay? And it's got some value in it at the moment. Now, during my function, I'm going to do something. I'm going to copy time delay into a variable called count. Okay, doesn't matter what these are called, okay? And my ISR, I'm going to increment. Well, increment's not the right word, of course. I'm going to use time delay plus. So again, I'm trying to explain the issues with, just focus that a bit. I'm trying to describe the issues with atomicity. So time delay has got some value in it. Who knows what those bits are? And we are at this stage of copying time delay into count. Well, count, of course, is another variable in memory, and it's also 16 bits. So let's think about what this copying process is. It's sort of like least significant bit to least significant bit. Now, it doesn't actually happen like that because the ABR doesn't copy directly between memory. It copies between memory and registers and between registers and memory. So the least significant bit goes into the least significant bit of a register, and then it goes into the least significant bit of count. So this is time delay. So there's two operations: copy it into the register, copy it into count. And then the next thing, of course, is to copy the most significant bit into the register, right? And then copy that into the most significant bit of count. So we've got at least 1, 2, 3, 4 operations taking place. These are machine cycle operations. Of course, this is just our C code, which is a single, very simple line of C code, but is actually going to translate into at least 4 operations of the machine cycle type microcontroller code here. So what that happens is, if we are halfway through this process and we're at this point here, we have copied the least significant bit of this variable into a register, and then the interrupt occurs and we increase this value. Well, hold on. What if this value was 255? So we've copied 255 into a register, then we increase the value, and this becomes 256, which of course in binary speak means that this is 1 and this is zeros. So this has gone from 255, 1, 2, 3, 4, 5, 6, from 255 to 256. So, but during this time of the interrupt, we've already copied the 255 into our register, and then we get the interrupt and it increases it from 255 to 256. Now you can see what the problem is. It's going to finish the interrupt and then go back to this point in time and copy 255 into here. Okay. And then what it's going to do is it's going to copy the 1 into our register, and then it's going to copy the 1 into here. So that then becomes, you know, the binary number here has suddenly changed. We no longer have 256, right? It's completely different. So again, just running over that, what's happened is we've got a number in here which is 255. We copy it into a register, our interrupt occurs, and this number becomes 256. Then we go back to processing and we copy the 255 that's in the register into count, and then we continue by copying this into here, and you end up with, of course, not 256. So we've got a real big problem here. And this is all tied up with the atomicity of our microcontroller. What's really happening is we're working at 8 bits at a time. And when you're doing atomic, or actually when you're doing non-atomic operations, which is what this is non-atomic. In other words, it's not operating at the level of our microcontroller. So I'm just going to go back to sharing my screen again. Let's pop this back up here, and I'll go back to screen share. Where's that gone? Here it is. Right. Now with my little pointer. Right. So what we've done is halfway through our operation of doing this copy, we've increased the value. Now, it doesn't appear that that would happen, but it does happen, okay? So what do we do? Well, actually, if you're doing non-atomic operations inside an interrupt, then you should disable the interrupts from occurring at that point in time. So we're going to be, we know that this time delay is a non-atomic, the copy is non-atomic, and that time of delay is used here. So that's the two things. It's non-atomic and it is used in the ISR. Then we should disable the interrupt from happening while we're doing this. And this is really important. And of course, you could just do the global command, which is just disable all interrupts while you're doing this. And then when you've finished, you enable them again. So that's what we can do. We can disable the interrupts, do our non-atomic operation because that variable is part of an interrupt service routine somewhere, and then go on and do and enable our interrupts again. So this is how you would protect this sort of critical problem from happening. Now, there's something else I just want to draw your attention to, and that is the word volatile. Again, this comes back to an understanding of the fact that the microcontroller is compiling your code from C into machine code. And during that, it's making all sorts of estimations about what you are and aren't likely to do. In fact, there are different options in the optimization for the compiler, which say, hey, I think I can do this better than the person who wrote the code, and that's what the optimizations are all about. But in this situation where, for instance, time delay is used here in the ISR, and it's used here in the function, the compiler is going to think, you're not actually using time delay. I'm just going to get rid of it for you. And it might just delete the line of code for you. And so one of the things that you can do is you can signal to the compiler that this is a special variable that I do not want you to optimize. And that's what the word volatile means. It signals to the compiler, don't mess with my variable, okay? Don't mess with my variable. That's a really important thing here to take away from this about interrupts. Now, why is that? I've lost my selection. Here we go, let's put this all on one line. Signals can compiler, don't mess with my variable. So what have we looked at with interrupt service routines? We looked at the fact we've got a couple of pins. We have looked at how we can use these interrupt pins to sense non-synchronous or asynchronous events in the real world, stop our program in the middle of this other processing it's doing, and then take care of that non-synchronous, asynchronous event, and then go back to its normal processing. Of course, it doesn't come without complications. And we've looked at the different complications, and one of those, of course, is atomicity. So I just want to sort of, thinking again about why we're using an interrupt to make our system more responsive and reactive. And when you keep that goal in mind, then in this case, you're also going to be able to look at these interrupts and think, is this really achieving what I want it to achieve? And is it doing it in a safe and critical way? Okay, so this finishes the little bit on interrupts for this week. Cheers.